Okay. Lesson 18 to 20. So this is lesson 18. So exponential functions. So for this one, guys, you guys have probably, well, actually, to tell you the truth, this one is actually pretty timely with coronavirus because this is what we keep hearing about, like flattening the curve, right? So we have this situation where we have a graph, and on this side we have, like, number of cases, and on this side we have time, like on the X one. So what it started out like, especially like, in Alberta, it started out pretty flat, right? It started out like, down here, going down, down, down. But then the way this works is that, they're not sure about the numbers, but like it's, one person can infect like, two to three people or something, right? What that means is that, like, and that would have a time frame. So that would be like every 2 days or 3 days or something like that, right? But either way, whatever that time frame is, it starts out pretty slow, going up and up and up. And then over time, it actually goes up faster and faster and faster and faster. And that's what, when they're saying this thing could get like really out of control if we're not careful, is that if you think about the distance that, like, if this was in days, right? Maybe this was like day 30, right? And this is like day 31. Then the difference between day 30 and day 31 is huge. And then the difference between day 31 and day 32 is extremely big, right? Because it goes up exponentially like that. Like these exponential, it's not very intuitive. We have a hard time thinking in exponential graphs, right? So that's the idea. It doesn't actually work that way where it goes up forever, though, right? The way it would work is it goes up exponentially for some time, and then it'll start coming around, right? And then eventually it would go back down again, and then we'd have something flattening off where we had no cases in the end, right? So it would be a curve like this. And that's what, I don't know if you guys keep hearing on the news, they talk about flattening the curve, right? What they're trying to do is they're trying to, even though it might still be the same amount of people that get it over time, what they're trying to do is, instead of it spiking like this, they want it to go up like this and then down, right? So they want to flatten the curve. They want to make sure that we're all under this. So right now, during the time of this video, we're in a case where this thing is going up, right? Like every day we're still going up and up, right? We're getting more and more cases. And it's hard to tell, is this thing going to keep going up like that and then come around that way? Is it going to come around like and flatten like that, right? Like there's so many different situations here that we don't really know what's going to happen at this point, right? Everybody's hoping that it's more of the bottom case and not the top case, but we're not sure, right? But this is really, like, when they're doing their equations to figure out what's going on, you can bet they're doing a lot of the stuff that we're doing, that we're doing right now, right? A lot of the same ideas. So, okay, so characteristics of exponential functions. All right, so here's the idea. So it's all going to be based on this equation. This is on your formula sheet. Y is equal to a and then c to the power of x, where c would be, well, we'll talk about this in a second. So in this case, we're going to start off, let's say, with just the function 2 to the power of x, right? So notice when we graph this now, right, that x is actually up in the exponent, right? So that's going to change things a lot. So we'll kind of see that in a second, how that changes things. So in this case, if I'm looking at this, right, at this graph, well, if I had 2 to the power of 0, right? So this is like 0 is my x value, and 1 would be my y value in that case, right? Okay, so that would be, right at the beginning. And then when x is equal to 1, then y would come out as 2, all right? On the next one, when x is equal to 2, y would come out as 4, and so on, right? And this gives us that curve that we're used to. Now, that's going to be on the right side of the graph, like, because we started that x is equal to 0 and then went up, right? But if I start going on the left side, right? Left side, right? So going this way, so my x values are going negative. Well, what's going to happen there, right? Let's get back into negative exponents and what that means, right? So if I had y is equal to 2 to the power of negative 1, so my x value is negative 1. Remember what a negative exponent does. A negative exponent flips this, right? So this was really 2 over 1 to begin with. So what that would do is that would flip that around. That's actually 1 over 2. So notice that my y value actually got smaller, right? So when I put in -1, now I'm at a half, right? So that's just what this is. Now, if I put in y is equal to 2 to the power of -2, okay, well, that would be y is equal to, and this was 2 over 1, so that's now 1 over 2, still to the power of now positive 2. Well, that's really 1 over 4, right? You could square the 1, which is still 1, and then square the 2, which is 4, right? So if we, I think we got enough that we can start to kind of graph this thing. I think it'll make more sense when you look at the graph. So here, using these numbers, when x was 0, y was 1, right? So when x was 0, y was 1. That crosses right through the point, and we should write this one down because it actually is a really important point to note here, is the point 0, 1, right? That's typically where it's going to cross. If we don't change, well, I'll talk about this in a minute, but if we don't change the a value, that's where it's going to cross. All right, so now when x is 1, y is 2, right? We did that from this one. Okay, so that's going to be when x is 1, y is 2. So that's going to be right there. Next one there, we said when x was 2, right? So y is equal to 2 to the power of 2. Well, that's 4, right? So I'm going to go to 4. Next one, y is equal to 2 to the power of I got to add myself, 2 to the power of 3. Y was 8. So that's going to go up to 8. And there's that standard curve, right? There's that signature exponential curve we have going on, right? And this one kind of makes sense in the positives, right? But now going the other way, when x was -1, remember that was a half, and then a quarter, right? And it goes down and down and down and it never actually touches, right? We get closer and closer to 0, but never actually touch 0. So that is an asymptote along the point y is equal to 0. All right, so just writing this all out now. So there is our standard graph, right? That's typical of what we're doing here. The domain of this guy is going to be, well, x is a member of the real numbers, right? It can go infinitely far to the left or negative, infinitely far to the right, right? So that's fine. Our range, though, of this graph, y has to be greater than 0. Not greater than or equal to, because it never touches 0, but just greater than 0. X-intercepts, none, right? This thing never crosses the x-axis. Y-intercept, in this case, it was 0, 1 for this graph. And then the end behavior, well, the end behavior, it's written different ways. You'll see different textbooks and different teachers say it different. But really the idea here is that in this quadrant, in quadrant 2, right? If you remember your quadrants, this one's quadrant 1, quadrant 2, quadrant 3, and then quadrant 4, right? So you could say low in quadrant 2, low in Q2, and high in Q1, right? So just means it's getting like low, like toward the bottom of the quadrant, and then really high in that quadrant. But like I said, you'll see that different ways. And then asymptotes. So we have a horizontal asymptote at the point y is equal to 0, right? The x-axis, right? Okay, so what is the significance of the asymptote? So really, pretty much everything we said. Like you're never gonna touch that asymptote. You're never gonna have the negative numbers either for your y values coming out the bottom. But yeah, we talked a bit about that already. So all right, next one. So now, now that was a value, like a c value. Here, I'll write this again. So it's y is equal to a c to the x, right? So the last case was a c value of 2, right? So that would make everything get bigger, right? Because I'm going 2 times 2 times 2 times. It's going up and up and up. Like, you know, every number is doubled every time, right? But here's the other situation: is if we have a c value, so that value between 0 and 1, right? So between 0 and 1 could be something like 0.25 or 1 over 4, right? Like some fraction that's going to give you a number between 0 and 1. Okay, so if that was our c value, that's actually going to change things up a little bit. So, you know, you can look at this. Let's, I'm going to give you some examples here though too. So let's say we had, 1 over 4. So let's say we had y is equal to 1 over 4 to the power of x. Okay, well, let's throw some numbers in there. So let's say y is equal to 1 over 4 to the power of 0. Okay, maybe I should have said this in the last one too. Maybe you kind of forgot this one. Anything to the power of 0 is just 1. So we are still, at this point, going to cross through 1, right? But let's go y is equal to 1 over 4 to the power of 1. Okay, well, that's easy. That's just 1 over 4. All right, so that's just going to be when x is 1, y is 1 over 4. So that's different, right? Last time it was going up, now it's going down. The next one, y is equal to 1 over 4 to the power of 2. Well, y is going to be 1 over 4 squared is 16, right? So that's really, really close now, right? And I think you'll get the idea that this is my asymptote now. Now the asymptote is going to be on the right side of this thing, right? Going down like better than I'm drawing like that, right? Now what's happening on the other side? Maybe you can figure that one out. Let's put in y is equal to 1 over 4 to the power of negative 1. Okay, so remember a negative exponent, what that does, that just flips these two guys. So we get y is equal to 4 over 1, or just 4. Okay, so when x is negative 1, y is 4. All right, I think we got the idea, right? You'll have the same type of situation as for the next one, but that is what's going on here, right? It's actually flipped. It's going the other way now than it was before. So that's going to be the case whenever you have a c value that's less than 1, but not negative. You won't have negative there. Yeah. All right, so the domain of this guy, x is a member of the real numbers. Range would be y is greater than 0, just like the last one. X-intercepts, none. Y-intercept, again, right, because anything to the power of 0 is just 1, then the y-intercept was still 0, 1. The end behavior, you'd say high in Q2, quadrant 2, and low in Q1, quadrant 1. And then the asymptotes, we still have a horizontal asymptote at y is equal to 0. Okay. So that's pretty much the gist of it. So let's carry on here. So now a couple of weird cases. So I kind of want to go through each of these. We don't do these too often, but it's worth kind of going through to get the theory of it too. It said, what about this? Like, what if c was equal to 1, right? What would that look like? Well, let's just put that in for a second. I think it'll make sense. If I have y here, y is equal to a c to the x, right? And I just left out a for a second or made it 1, then that would be y is equal to 1 to the power of x. Well, that doesn't matter if I put 1, 2, anything in there. That's always coming out as 1, right? So no matter what the x value is, the y value is stuck at 1. So that's the way that graph would look. Now, the next one, this is kind of a strange one. So this would be y is equal to, so we'll say 0 to the power of x. Okay, well, in this case, if I put in y is equal to 0 to the power of 1, well, that's actually just 0. 0 to the power of 0 actually ends up being undefined. You can't actually do that one. And then if I did the other way, right? So if I went y is equal to 0 to the power of negative 1, well, one way of thinking about this is that that's like 0 over 1, you could say. And then if I flip that upside down, I'm going y is equal to 1 over 0. Well, I can't divide by 0, right? It like flipped the 0 down to the denominator, which you can't do. So it's actually not allowed to be over here, right? So in the end here, this graph just looks like this, right? So it'd be stuck at 0 for any of my positive x values, and it can't be negative and it can't be 0, okay? All right. Okay, c is less than 0. So an example of that, let's say if like c was equal to negative 2, well, then that would be like y is equal to negative 2 to the power of x. And you'll see some weird things here, right? If we made a table of like x and y, and we put in, let's say, negative 3 in for this one, well, negative 3, that would come out to negative 1 over 8. Right? Because it would flip it upside down, and then 2 to the power of 3 would be 8, so it would be negative 1 over 8. But here's where it gets weird. If I put in -2 in for x, then what's going to happen there? Here, let's actually do it so you can see. Y is equal to -2 to the power of -2. Okay, so this negative here is going to flip it. So that would be y is equal to 1 over -2 to the power of 2. And then it's right here. -2 squared, this actually comes out to +4. Or is positive 1 over 4, I should say, right? So it came out positive. So that makes it kind of strange. So that came out positive, and then -1 would come out as -2, 0 would come out as 1, and we get this back and forth pattern of negative, positive, negative, positive, negative, positive. So that's 4, and then 3 would be -8. So like I said, this is kind of a weird when you graph this thing, this is the way it would look. Is that so at -3 it'd be -1 over 8. You'd start there. We'd jump over to the other side, and we'd be there. At -1 would be at -2, and then at 0 would be at 1, and then down to -2 for that one, and then back up to, so at 2 we're at 4, and back and forth, right? It just does this really strange pattern, and then back to -8, right? So it's just a back and forth thing. We can't even actually connect these dots because it's not that it does this, right? Like that's not the case. We just have to leave it like those dots where they're not connected. But yeah, we won't be doing a lot of those because they're not standard. Okay, so let's do this one. So it says determine an exponential equation in the form y is equal to a c to the x, where a is equal to 1. If you haven't noticed yet with that a is equal to 1, what that would do, we're going to talk more about this in the other lessons too when we start doing our transformations. But our a value really is going to be, well, that's your horizontal, or sorry, your vertical stretch factor, right? It's like the number out front of the function. It's even called a, right? So a has always been our vertical stretch factor. It still is. So if that thing became a 2, what that would do is it would multiply every number by 2, right? That's the idea there. But they're telling us, okay, we're not going to stretch it at all. So it's just a is equal to 1, okay? So the way we can do this is I'll write out my equation and say, okay, y is equal to, and then, well, okay, a is 1, so I'll just put 1 or don't put anything, and then c to the power of x. Okay, well, looking at this graph, I just don't know what the c value is because I don't know how fast it's rising, right? But they were nice enough to give us a bunch of x's and y's, right? They gave us this point and they gave us this point. That's actually more than we needed. We only actually needed 1 point to make this work because we also knew that it passed through the point 1, right? The y value is 1. So there's an x value and there's a y value. So let's just plug those in. So our y value here would be 27, and then c to the power of 3. Okay, well, we can do that. So this is c to the power of 3. If I want to get rid of that 3, I'm going to cube root it. So cube root both sides. So we end up getting c is equal to 3. So, therefore, our equation here is just y is equal to 3 to the power of x. And that's it. All right, next one. So this will be similar. So we'll start off by saying y is equal to c to the power of x. And then I'll use these. I could use either, but I'll use this side. So we'll say, okay, there's my x, there's my y. Okay, so I'll say 625 is equal to c to the power of -4, right? Because x is negative there. So in that case, let's clean this up a little bit. I'm going to rewrite this as what c to a negative power actually looks like. Let's rewrite this as 625 is equal to 1 over c to the 4. Okay. Now I'm going to get that one out of the denominator. I'm just going to move it up here. So I'm going to have, well, actually I'll do 2 at once. I'm going to move that up there and I'm going to move 625 down there. So we get, not 6, c to the 4 is equal to 1 over 625. Okay, well, what we do there is we take the fourth root of both sides. So fourth root, and that will end up being C is equal to 1 over 5. Okay, so in the end here, we get Y is equal to 1 over 5, in brackets, to the power of X. So there's our equation. Okay, now I'm going to show you guys a little bit of a tougher one too. And what would be tougher about this would be the case, what if we didn't know what A was, right? They told us it was 1, but like, let's say you couldn't actually tell that from the graph. Maybe they just gave you these 2 points, right? Let's actually do that type of a question as well, and see if we can get to the same answer as before. We should get like an A value of 1 and a C value of 3. So in that case, what we're going to do, try to find enough room. Here, I'm going to do it over here just so I can still see the graph here. So we're going to do it for both of these cases. So here, I'm going to write it out. We'll say Y is equal to A C to the X. Okay. And I'm going to write in what I know using this point. So I'll say, okay, well, the Y value was 27. And I don't know A. We're pretending we don't know that it's 1 now, right? So I don't know A. And I don't know C, and I know that X is 3. Okay, so here's the problem. I have 2 unknowns at this point. Well, if you ever have 2 unknowns, you just need 2 equations and you can solve for those unknowns. So let's make another equation, and we're lucky enough that we have another point, right? We can make another equation with that point. So here's equation number 1. So we'll just put that aside for a second. And we'll do equation number 2. So there's an X and there's a Y. So my Y value is 1 over 3 is equal to A C to the power of -1. All right, here's what we're going to do. I want to rearrange this so that it says, well, so there's one equation. But I'm going to rearrange this one, my second one, so it just says A is equal to something. So here, this is 1 over 3 is equal to A C to the power of -1 really puts the C down to the bottom, so that's just A over C. Okay, so that's what that is. Now I'm going to move the C up to the top. So this is really C over 3 is equal to A. All right, so there's my equation. Now, I get to just put this one, right? That's what A is equal to. I get to put that guy in there. So we're going to rewrite that top one now as 27 is equal to, and instead of an A, I'm going to put in what A is equal to. So I'm going to put in C over 3. And then I've still got C to the power of 3. Okay, so cleaning this up a little bit, this is now 27 is equal to, and C to the power of 1 times C to the power of 3 is C to the power of 4. Okay. And that's all over 3. So I'm going to multiply that by 3. So yeah, we end up with 81 is equal to C to the power of 4. And then at this point, we'll go, okay, well, fourth root. So, and if you're unsure about this one too, and if you don't know how to do, some of your calculators can do this right away, but you can go 81 to the power of 1 over 4, right? If you actually did that in your calculator, you get the same answer. Or take the fourth root, it gives you the same thing. So 81 to the power of 1 over 4. So we get 3. And that's what we were expecting, right? It was 3. So that's our C value, right? So we figured out our C value. So far we've got Y is equal to A C to the X. And now we can say either one of those points. So I'll put in, like I did before, we'll say 27, right? Just one of those points is equal to A 3 to the power of 3, right? Yeah, 3 to the power of 3. Cleaning this up, we get 27 is equal to A times 27. And this is looking good. We were expecting 1, right? We're going to divide both sides by 27. So 27 divided by 27 is in fact 1. So our equation is, in the end here, y is equal to 1 times 3 to the power of x. So that would be the harder way if they weren't nice enough to tell us that a was equal to 1 from the beginning. But the other thing we could have done, right? If, again, if they were nice enough to show us, if you can see that it crosses the y-axis at 1, then we could have known it was just 1 to begin with, right? That like it will always, if your a value is 1, then it'll cross like at 1, right? If you can see that it crosses at 3, then your a value would, no, that's not 3, at 3, then your a value would be 3. But the way I did it here was as if we didn't know where it crossed the y-axis. Okay, that took a little longer than I was expecting. So let's move on to the next one. This one's not too bad. So next one here says, all right, so a filter removes 70% of impurities from water that has passed through it. Multiple filters can be used together to increase the purity of the water. This situation is represented by A is equal to 0.3 to the power of n, where A is the proportion of the impurities remaining and n is the number of filters used. Explain why the base of the exponent or exponential fraction is 0.3, right? Well, why it's 0.3, right? This is actually 30% of something. If I wanted to figure out what 30% of something was, then you'd multiply it by 0.3. And why am I multiplying it by 0.3 or 30%? Well, that's because the filter removes 70%. So really, if you had 100% of something and then subtracted 70% of something, you would have 30% of it left, right? So what we really want to do is figure out how much 30% of the original impurities are, right? So in the end, what you would kind of do, that the general way of stating this is you'd say, you know, y is equal to that a value again, which we don't know, times, and then 1, right, like 100% minus 70% of x. So y is equal to a, and then this would be 0.3 to the power of x, right? Yeah. So we'll just leave it at that. Okay, so what's going on here then? So it says graph this exponential function. Okay, well, in this case, right, they never actually told us. So here's our equation. Y is equal to 0.3 to the power of x. Well, they never really told us. They never really told us what any of these numbers were, right? They never told us how many percentage or how many there were to begin with. So our y value here, what I'd want to make that one is actually, I can make any number I like actually, but I'm going to make that one equal to 1. I'm going to say it starts at the point 1, right? Like that's all of it. I can make it 100 or you can make it anything else really, but I'm going to make that the point 1. So that's going to be when x is 0. That would come from this. Y is equal to 0.3 to the power of 0 would give you the point 1, right? Okay. Now, if I change now for the next one, y is equal to 0.3 to the power of, and I'll make my x value 1. Okay, well, that takes me down to 0.3, right? That's at the point 0.3. And then the next point would be, you know, when x was equal to 2, and you'd end up with something like this, and then something like this, and then something. And we get that standard exponential graph going on. And it would approach 0, but never touch, right? All right, so now, oh yeah, sorry, but I made a mistake here. We actually shouldn't connect the dots here. And the reason why we shouldn't connect the dots is because this is actually discrete data. It's not continuous data. And what I mean by that is we're never adding half of a filter or an eighth of a filter or anything like that, right? It's either I have one filter or I have the next filter or the next filter or the next filter. There's no in between going on here. So this is discrete data, not continuous data. So you would leave the dot, like you wouldn't actually connect the dots there. Okay, what are the domain and range? So the domain of this, you would say is n is greater than 0, right? Greater than, oh, sorry, or equal to. It could be equal to 0 too. You could have none. And that's typically how you'd leave it normally if we were dealing with continuous data. but we're not, right? So I'm going to say where n is a member of the whole numbers, right? Because that's accounting for all my jumping, right? It's not connecting it. It's not integers. If it was like, or yeah, it's not real numbers there, right? Where it could be anything in between. So it's just the whole numbers there. So, okay, the range. So my range here would be, okay, well, y has to be greater than 0, not equal to, just greater than. But then in this case, it also has to be less than or equal to 1. And what that means, right, is that like typically this graph would, start into the negative, but I can't have negative filters. So the real world is putting this part of the restriction on it, that I can't start with negative filters. It's fine for the equation, right? Like if I actually graph this thing, you would see this backside of it, but the real world happening, I don't have any of that on the backside of it. So less than 1. Okay, so now what proportion of impurities remain when 4 filters are used to the nearest 10,000? Is there an actual number of filters that will remove all impurities? Okay, so in this case, we're going to say 4 filters. That would just be y is equal to 0.3 to the power of 4, right? That's our filters is the exponent. So this would be y is equal to 0.0081, which is, if you multiply by 100, right, to get the percentage, that would be the same thing as 0.81%. Okay, so that's how much you would have left in that case. And will it remove all impurities? No, right? That would be touching 0, and we never do touch 0. Okay, and that's it.